Okay, already one too far. Okay, hello everybody, and I know it is tough to have the last speech before lunch. Maybe it's only topped by having the first after lunch. So, but I do my very best, and I'm heading the Department Interactive Media at Fraunhofer HHI in Berlin. I'm going to present you 3 challenges today, and 3 mainly unsolved challenges. And I want to share, I don't claim that we have solved it, but share a humble progress we have made in them. So what's the first challenge? The first challenge is what we call keyword search for images and videos. For example, if somebody wants in a real huge number of images or videos, find something like a picture containing a couple during sunset. That's tough. The second thing is, we have already heard about these petabytes of data. Most of them are movie data, are video data, and who knows what is in a video unless you have seen them, and that is time consuming, at least. And the third challenge, that is the 3D realistic visualization. We already heard a bit about that. I will tell more about it. But coming back to the first, what did we do? Image retrieval. And if you have a look over there at these 4 images, just guess, what do they have in common? If a human brain is going to analyze that and you want to add a tag to it, what is common? We come back to that. So, come on. What's now? Okay, we have this growing number of visual assets. And of course, there is an easy way to do it. It is just do a keyword-based search as we search on the internet. But this requires normally the textual annotation of images. And of course, who does that for his own images? Hardly anybody does it. And if you do it on a more professional level, it is also hard because you will have errors, it's labor intensive. And I'm talking here, you know, about these databases of professional stock image supporters. They have maybe 100 million of images. Most of them being legacy images, which are not annotated. Okay, what can we do? Wouldn't it be nice if we find something that gives an automatic semantic classification? So just somehow understand what is in an image, a bit like human analysis would be. And there's some progress on that. Yeah, you figured it out. They have in common that they are vehicles, but how to do that for a computer? But this is the example I want to give you, what can be done. So our example pattern or example tag, as we call it, are flowers. And you have some flowers, and it's a 3-step approach. The first step is the training phase. Find common visual features in a known and manually annotated set of images of flowers. And then you can give something what makes it a flower, and that is symbolized by the tag. And if you have this database, you can compare a new image of a flower. That is now the untagged image that comes in. And it will automatically be tagged by flower. Of course, there will always be errors in that method. And this enables you, now this is the human who goes for a search, and the search is done in the traditional way that it's just a word search. And that is step 3. These categories that have been automatically annotated after a training step can be used for searching. Well, basically, that is the solution, or that is the thing we did. And then maybe the outcome is something like a picture that can talk or can be tagged by these tags. So we know this is an outdoor situation. It is very likely to be during the day, not at night. There is a vehicle in it, it's city life. But you see, in the raw data, that comes just with the likelihood. It's a percentage, and you can never be sure on that. And the next step would be now give it, maybe we cut with the likelihood of 60% or 70% or something. Okay, where are we today? We did that with a quite huge set of categories, 93 categories, which are a bit standardized in some competition we went into. But this approach is very generic and can be extended to other categories if you want to add some. What makes it difficult is, well, the performance, the quality of the outcome depends on the training phase, and it depends also on the vehicle example, the intra-class variance, and there are some tags that are easy. If it's a person or if it's a beach situation, could be figured out automatically. But whether this is something like melancholic, it's hard to decide. Even humans might argue about that. Okay, we got really good results on that. There are international competition, and we have been amongst the first of these competitions. There's one slide for the background on that. We might go into detail later. So the background is basically you add a visual bag of words for those who are familiar with that, and that is done by what is called the histogram of gradients. So you analyze an image by really thousands of histograms, and then you categorize them into, yes, they belong to that tag category, or no, they don't. So, sorry for that. So that is the first challenge and where we stand on that. The second thing is also, again, what if we have video data? And we go into video data. We produce tons of gigabytes from surveillance cameras. I figured out that every minute in YouTube there is an upload of 35 hours. How could you learn? How could you see what is in these videos? You don't know the contents. And you can't do that manually. So we went for solutions who give something like a visual table of contents for video data. And that is exactly like it is done on a book. In a book, you can go on the first page, second page, and you can skip through, and you have a certain impression of what's in the book, and then you can decide whether it's important or relevant for you or not. Let's try, okay, and that is into chapters, paragraphs, down to letters. And let's try to migrate that idea to a movie or to a video. And you have several movies, and they split down into scenes. They go down into shots, subshots, and at the end of the day, you have the single keyframes you hardly won't be interested in. And if we find out that structure, we could give a visual table of contents also for visual data for movies. And well, it's nice, it fits to what we have seen. That was a test movie with a geologist who is out in the field, as we have seen it before. And then it splits down into the scene level, and it splits down into the shot level. A shot is a continuously taken part of a movie, and whatever it is in, it's not that important, but you get an overview. And if you have a good keyframe representation for each shot, you can be nearly absolutely sure that you don't miss any significant part of that movie. Okay, and that is the temporal structure of a video is found and analyzed, and the most relevant keyframe serves as a representative for that part of the movie. Where can you apply this? Well, it makes browsing so easy. You have a preview, and you save really a lot of time not to go through that video, but you have this kind of preview, at least visually. Or you could do something like editing. You know exactly the temporal units. You can shift them, you can delete them, you could rearrange them. It's great to use that. And again, one slide on how can that be done? I will restrict myself to some of the methods we use. Again, if these are the slides of one shot with the fish, and then you move over to the second shot with the flowers, you will have a distinct discretion in the histograms. So the color histograms will be extremely different between the first and the second step. And that gives you a clear cut between the two. Similar if you go for the scene detection, but you have to do it a bit more tricky. We found out that the scenes have a high coherence if it's in the same scene, and there are rarely certain gaps if it switches to another scene. Okay. Point number 3, I promised something about 3D data. And we have heard that, thanks for that good examples we have seen on huge amount of data coming from. We have seen a lot about simulation. We have seen some medical data, or we'll see them later. There are a lot of data in biology and many other fields. But at the end of the day, most of these 3D data are flattened on a flat screen when you display them. And we try hard to overcome that, especially when the data is complex. The higher the benefit, and now it comes to stereoscopy, is the more complex these data are. All right. Okay. Dealing also with time plus 3D, sometimes called as a 4D data even. Now I want to give you a bit about the 3D. We have heard about glasses, and not everybody uses it. There's a nice image of your president, or the US president, using the glasses, and he looks pretty fine with them. And some know probably we have a similar image of our chancellor, and here it is. And that is always a wonderful reasoning to go into the autostereoscopic stuff. If not convinced before, you're convinced now. Coming a bit back to how is it done? I have to give you this view over here, because this is exactly what we do outside with our exhibit. And I will be asked many times. I do the explanation once for all of you, and don't ask me later. But you have the left eye and the right eye, and you have lenses in front of the display. That's the display panel. You have the left and right image. And if you do the geometry of the lenticular lenses right, then you can bend the rays from the left image into the left eye and from the right into the right eye. And that's the basic trick and clue for all of these displays. Of course, you can do different barriers. You can do more than only 2 views, all that stuff. You can do some temporal interlacing, but that's it. And the big drawback of that solution is if the left eye is moving to the position of the right eye, the stereo effect is gone. So this point where it works is called the sweet spot, and that's limited, because human eyes have just a distance of 65 millimeters. Okay, but we have found a solution for that. Now think, that is the view for the right eye, for the left eye, and this person, unfortunately, is moving. Well, the answer is we have to move the view for the left and the right eye in the same proportion and same direction as the person is moving. So that comes down to this. I'd put it like that. The viewer is moving the head. We have to find the head position. We have to calculate where to steer the left and the right view to, and then we have to update that direction. And that has to be done faster than the head is moving. Okay, that is exactly what you can see outside. Oh, even 5 minutes, that's good, yeah? I thought less. How did we do that? How did we steer and control the direction of the left and the right view? First, we have to go into, and I hope that movie works. Yeah, pretty well. That is Frank Neumann in our team, and he is really trying also to fool a bit our eye tracker. But It's fast, and it's rather precise. And you are invited to, yeah. It's so precise that it even goes for printed images, and you will see printed images later. Of course, the challenge on the eye tracking is you have to make it robust. There are illumination changes, there's skin color, there are glasses, there are birds, and so forth. But under some controlled condition, it works pretty well. And then you do something that is depicted over here. I said about this tracking, but how can the tracking be achieved? What is the variable parameter to do it? Look closely. First, in the beginning, the green eye is seeing the green pixel, and that's a barrier. Now, unfortunately, the head is moving, and now the green eye is seeing the blue pixel. That's bad. That's reverse stereo or nothing. But if we just shift, look up here, if we just shift at the same time the pixels to the left and to the right, then the green eye is seeing again the green pixels. It's a bit more complicated in reality, but basically that's it. And to repeat it, we have a barrier. We make the shift as fine as possible. So try to make very, very small shifts, because otherwise you end up in discrete jumps, and that can be seen. And you have to accommodate to 2 or 3 directions, because the person can move left, right, up, down, or forth, back. And you have to squeeze the pixel, for example, if somebody is moving closer to the display or stepping back. But that's it. And that is one of the displays we built based on this idea, very similar to the one we are presenting outside. Yeah. Then we did something else. I skipped through that, but there are more ideas that can be put on top of this basic idea. There's just one last I want to share, and this is eye tracking can be reused. I'm talking about eye tracking for stereoscopic output adaptation. You could use that also for motion parallax simulation. Motion parallax simulation is a monocolor depth view, but it can be done just when you know where the eyes are, you can have this look around effect. Yeah? And that happens in the real world and is very important for a realistic stereoscopic impression. I give you the video, and it's also a stereo image you can see, but now there is Judge Clooney, and he's literally turning the avatar's head. So that is the control monitor. You can see what we show as a virtual person, and it follows exactly in a look-around effect to where he is positioned. And these stripes come from the fact that it is a 3D display. It's an artifact you won't see if you stood exactly in front of the display. Okay. That's the theory, that's the data, and that is the last to make you laugh. The display has been approved by the US police, as it is in our Boston office, and hope to see you at our exhibit at the booth. Thank you.
Questions for Ulrich?
So what it takes that from individual, what we call it, systems to becomes a more group ones right now, because without the glass you just have to control one person eyes tracking. Now if you have multiple people, multiple depth, and how where we are standing on that one.
It's not so easy to extend that approach to just a couple of people standing in front of the display. Tracking would be easy, but having output for more than one is hard. There is a European project, Jürgen mentioned it. They went for 4 persons who get their individual image. So you go into time interlacing of the images, but that is an advanced research topic. So I'd recommend for the time being, if there are more than one, go for a multi-view display, and you're set with that. Yeah.
Good. One last question. Gentleman in the back.
Come.
Oh, I'm sorry.
Should I go?
Okay, that's fine. Go ahead.
So I have a question about the first two projects, and it's a very similar
Great, yeah.
kind of question. Are you using purely signal features from the video and images, or are you using some sort of high-level features like film grammar for shot detection, or some sort of photographic composition rules like the rule of thirds for image annotation?
Regarding the shot detection, it is really detect the transitions of one shot to another. It's easy if it's a cut. It's difficult if it's a dissolve or a fade here.
Yeah, I was wondering if there was sort of, because in film grammar you would have things like from a conversation sequence you switch to like some establishing shot, and
Yeah.
then you go zoom in and then zoom into the details, and there might be some sort of higher level feature that you could extract if you were to consider film grammar.
Yeah. Not really yet. What we thought about, but we didn't do it, is if you combine the visual clues with the audio clues, that would help. For example, if it is a news on TV, that could help a lot to analyze in addition the audio stream.
Thanks.
Okay. Thank you very much.